Well, hello, everyone. Welcome to the webinar. Now you see it, now you don't. The magic of dry ice in medical device manufacturing. I'm your host, Paul Dvorak, founding editor of Medical Design and Outsourcing magazine. Thank you for joining us. Now, before we begin, let me cover a few housekeeping items. Let's start at the bottom of your audience console. You'll see several application widgets. For instance, when a question occurs to you during the presentation, click on the Q&A widget and type your question in there. I encourage you to ask questions. Don't wait to the end of the presentation. Submit your questions as they occur to you. We'll capture all the questions we can and try to answer as many as possible before our time is up. So should a question deserve a fuller answer or we run out of time, it'll be answered by email. Now in the resource widget, the one that looks like a green folder, you'll find a copy of today's slide deck and additional materials. This webcast is presented using a slide deck and not a screen share or live demo. For your viewing comfort, you can expand the slide area by clicking on the Maximize icon at the top right or by dragging the bottom right corner. If you have technical difficulty, click on the Help widget, the one with the question mark. And lastly, if you don't see slide movement on your console, hit the refresh icon in your browser bar or hit the F5 key to refresh. An on-demand version of this webcast should be available tomorrow and can be accessed using the same audience link that was sent to you earlier. Now let me tell you about a speaker, Steve Wilson. He is the Director of Global Business Development, Plastic and Rubber for ColdJet, LLC. As a former plastic business owner, he has over 30 years of experience in injection and compression molding, extrusion, blow molding, thermoforming, and rotational molding. He began his career at Millicon's Plastic Machinery Division, serving in manufacturing, product line management, and a variety of sales and marketing roles. Steve is a published author and a frequent speaker at plastic industry events. He holds a bachelor's degree in business administration from Cedarville University and an MBA from Xavier University. And with that, let us begin. Steve, the microphone is yours.
Thank you very much, Paul. I appreciate that introduction and welcome, and thank you all for those that have chosen to join with us this afternoon. I appreciate your coming on board with us. I want to go through some brief things with you here with regards to the magic of dry ice as it relates to the medical device manufacturing industry. The dry ice itself is kind of magical. Now you see it, now you don't, as illustrated in this slide on the left. Now you see the various forms of dry ice as it's very commonly produced, and now you don't on the right. It sublimates, it disappears, it leaves no residue, and that part of the magic of dry ice will be very helpful for us in the dry ice usage in medical device manufacturing. That sublimation can be illustrated in this quick video with dry ice. Because you can see some rejects due to fouled cavities, clogged vents, and now you will not, because this will make it so much easier to do. It is much faster, so you can make more parts. You will improve your productivity using dry ice in manufacturing processes, whether or not you're molding or subtractive manufacturing, you're machining parts and you are post-deburring them. This will be faster. It is a gentle way to clean tooling, so your asset life, the mold itself, the tooling itself, will last longer. So you may be cleaning your tooling with traditional methods today, which could be wearing them out. It can save you money because it is much faster, so when you do clean, it will be measured in minutes instead of hours, and no more chemicals. This will unwrap the fact that there's no more things going into landfills. This is USDA, EPA will unwrap that one, but it makes for a better environment, improves worker safety, eliminating some of the cleaning methods that we're traditionally using in our industry. To unwrap improving quality, it is a better clean. Dry ice has a very low coefficient of friction, so it's able to penetrate surface small, complex geometries. The substance itself, the CO2, is FDA, EPA. I won't read those to you. Some of those are meaningful, and you walk under some of those regulations. But this is a food grade, same CO2 that we use to carbonate water. It leaves no residue behind. Some people in the medical molding are still using chemicals which may have kerosene as a base cleaner, and when you get done, you're either going to have to throw away, if you're molding parts, the next handful of molded parts, or you're going to have to follow that clean with a secondary clean, cleaning with alcohol. If you clean the first time, you'll get a better clean, and there will be no secondary waste, nothing to cross-contaminate the next molded part. It will keep all your cavities and vents clean. We'll unwrap that a little bit as we unwrap solutions, but it is a line-of-sight clean. It is a parting line clean for those of you that are molding, but we'll get into that. You're just going to get better quality parts because you're going to be able to be proactive. Oftentimes, mold cleaning is delayed. It's postponed because it's just not a fun thing to do. It's a tedious thing to do, and it's time consuming. So people wait sometimes until there's a problem, and now we're firefighting. Because cleaning with dry ice makes it so easy, it allows guys to schedule it ahead of time before the problems start, to be proactive, and you can eliminate a lot of molding problems that come our way in molding and manufacturing medical devices because of dirty cavities and vents. Some of those problems look like this. This comes from Femtech and some the sources down at the bottom, Sun Microsystems. These are just things associated with typical molding problems that we get when we have a clogged vent. I can end up with a short shot. We could end up with some flash because the vent was clogged. It's possible that if the vent is clogged, the air will actually start to jet. Some call it dieseling. It will burn the part, so we get problems there. It will actually damage steel. If the temperature rises as a result of that jetting or dieseling high enough, it can actually damage that portion of the mold. You can end up with just plate out on the mold. This particular picture is more of an automotive application where gloss control levels are a problem. But you can get plate out if the cavities are dirty. You just get flat out contamination on a part if the cavities are dirty. You can get splay as a result of having a dirty cavity. All these things can be proactively addressed, even down to the weld lines, just by cleaning the molds quickly and easily using dry ice. People who use dry ice tell us this. You can read these in detail later if you download this, but dry ice results in a superior clean. People tell us it allows them to clean areas that would not otherwise be cleaned. Those are in those areas that are down in corners, complex geometries of molds, just hard to get to with whatever you're using, a Q-tip or a pipe cleaner. It's just a more efficient way to clean with a better quality of clean, and we get a lot of feedback regarding that. You can improve or increase productivity. You can make more parts. I know the goal is to make good quality parts, but if we can clean faster, usually 4 to 6 times faster at operating temperatures, it allows us to make more parts, move on to the next scheduled device. It will take hours of downtime and replace it with minutes. It's not unusual for something to take 6 hours to take it down to 15 to 20 or 30 minutes of cleaning. This is why a lot of times cleaning is time consuming. It's a multi-step process, particularly if your molds are heated in any form. You go through this multi-step of pre-cleaning, all the sub-steps, the clean itself, then you got the post-clean, including just reassembling possibly and reheating things. We need to just stop the production, inspect, and move on. All those other multiple steps that are listed can be eliminated cleaning with dry ice. It just makes it faster and easier to do. And we get a lot of feedback from people. Like I say, I won't read that to you. You can read them faster than that. But people tell us they're able to extend their running times. They're able to reduce downtime because this makes it easier, and you get a good clean. So you will run and get better parts cleaning with dry ice. The third reason is don't wear out your tooling. Our tools are the heart of the whole molding process, whether you're pressure molding, injection molding, if you're extruding, whatever. The tooling is the life of the process. There's a company called Mold Tracks. They teach the tooling docs way to run the shop. They chart the different aspects of the process of what will wear out my mold. Cleaning techniques under the left side is right in the middle. How you clean your tool can contribute to mold wear. Cleaning with dry ice, one of the reasons we do it is to eliminate that step. There's no longer a need to wear on the cavity, on the vents themselves, with a variety of ways that will begin to wear the parting lines and the shutoffs, and then you end up with flash. I have all kinds of studies. I'll fly through this. We had studies done at Kettering University blasting standing still, just sitting stationary with dry ice at a 90-degree, 1 inch away, with no damage to the mold. That's not traditional blasting technique. For those of you out there that are familiar with it, there's always a traverse rate associated with it, but we did this stationary, in place for 60 seconds, still had no damage. We had a customer do their own independent study on wear and on thermal shock, standing on stainless steel, very common in medical device molding, and they did not alter the carbon particles at the core or the surface. They had no damage cleaning with dry ice. And people tell us that. It doesn't dull the tools, it doesn't destroy the metal, it doesn't change the metal, it doesn't roll the parting lines, it doesn't roll the shutoffs. Beautiful way to clean quickly without damage to the tool, without having residual waste. How gentle can you be? Now, this is from a TV show, the National Geographic Challenge.
So how much PSI is he using at this moment?
This is about 20 PSI and very small shape particles.
Punching a hole in it. So that's how gentle you can be using this process. At the same time, you can turn those pressures up and you can cut the card in half. But you have a broad window of where you can make this process. How gentle, how delicate you want it to be, or how aggressive you want it to be. And when we talk about the theory and the process, we'll unwrap that just a little bit more. You want to reduce the cost. It's important. What does it cost when the machine is down? That mold's only making money when it's running. This is just a simple chart, and you can probably look up where you are in the number of machines that you have in your facility if you're a molder, and what do you bill at. I think I've highlighted a 20-machine shop that bills at $50 an hour, and if they are wasting 15 minutes a day because the machine is down for preventative maintenance and cleaning, that type of thing, they are losing $63,000 a year. And you note the note at the bottom, that's a one-shift, 5-day-a-week operation. So it's important to know that downtime is costing money, and just knowing that 60 to 70% of your mold maintenance is cleaning the mold. So let's do it as efficiently, as effectively, and as quickly as we can. Once again, we get some feedback from various people. Talks about they dramatically improved productivity, helped them cut costs, reduce cleaning time by 95%. Those are pretty typical feedback for people who have chosen to use dry ice instead of traditional methods. It's a great way to improve environmental quality because it gets rid of chemicals. It gets rid of all those the VOCs that we have to deal with, the disposal issues of dealing with these chemicals and the regs that are used around them. Dry ice is a clean, sustainable process. There's no secondary waste. When it phases from a solid to a gas, the magic of that is it's gone. So you can eliminate the chemicals and improve the worker safety because they're not working with the caustic chemicals, which I won't go through and list all those. But you don't have to worry about having a worker exposed to dangerous chemicals any longer with the use of dry ice. You're not considered a greenhouse effect user unless you use 500 metric tons a year. That means you're ordering about 40 500-pound totes a week. I don't know anybody in the medical device or plastics industry buying anywhere near that amount of dry ice. This is an example that was done by Katie Wolf and her institute for the EPA. They were working with a company who wants to get rid of the VOCs in their plant. They were using this spray, this baseline hexane aerosol on the mold on a medical device. They were cleaning this tool. This is the way they would traditionally do it. And they chose to take a look at dry ice. These are some of the results they got. They were spending $56,000 a year. Talk about saving money. The dry ice cost them $6,198. Not only did they get rid of the VOCs, not only did they get rid of the environmental, but they saved money. Those cases and cases of aerosol cleaners were racking up. If anybody wants that, that's an independent study by Katie Wolf down there at the bottom. It's probably on the internet, but I've got copies of it, can send it to you. This is just cut and paste right out of her report. A lot of people, once again, tell us that, just to give you some data, very people that the worker safety has been improved, the whole environmental process is better, solvents have been reduced, productivity of employees are just up. Let's go into the introduction to this, what we're talking about, this whole dry ice, just in case someone's wondering what is this we're dealing with. Dry ice is simply the solid phase of carbon dioxide. All of this CO2 that we're using is a byproduct from an industrial process. Petrochemicals, distilleries, fertilizer plants. There are a variety of manufacturing processes that give off CO2. A gas company will build a plant right next door to one of these manufacturing companies. They will reclaim that CO2. They will scrub it to get rid of whatever smell may be in it. They'll pressurize it, turn it into a liquid, about 300 psi. Then they can transport it to a plant where they can put it in a pelletizer and literally turn that liquid back into a solid, CO2, and I'll show you a picture of that coming up. Just so you know, dry ice has been around for a long time. I'm not asking you to take a look at something that's relatively new and you're going to be the first risk taker. The ability to make dry ice has been around since the 1930s. The Navy's been doing it since the 1940s. A guy got a patent for it back in the 60s for taking meat off of a bone. Since about the early 80s, it's been used to clean tooling, or to what we're going to get into, actually deflashing, deburring parts as well. You see the beginning and the ending. There's a cooler sitting underneath both of those pictures. Still today, 80% of all the dry ice produced is used to transport cool. But we're taking a small part of it to use to blast with. CO2, just so you understand what it is chemically, why we use it, it's nonpolar, it's stable, it's not a bent molecule, as in water, which is in a lot of chemicals, or the chemicals themselves, which will react with the mold. It'll react with the carbon, cause it to rust. It's not bent, it's not charged. So it will not react with the mold at all. Just give you some chemistry to the CO2. And that's where it is made, right at about minus 78.5 degrees Celsius at atmospheric pressure. It will remain a solid. You get out under that curve where the temperature begins to rise once it's made, where the pressures may drop to just a tad, it will begin to sublimate. That liquid that was reclaimed from the gas is put into these copper tubes at the top of the pelletizer, the top left picture. Liquid goes in there, goes into that cylinder. That cylinder is a discontinuous process, but when it is stroking forward, it looks a lot like strand die extrusion, like a pasta maker. That liquid will flash into a snow at ambient pressure. That snow is then pressed through a die, and you make whatever size pellet or nugget that you want to make. Whether it's going to be used for blasting, which is 3 millimeter, it could be 6, 9, 12, 16, a variety of different sizes for transport cooling. The bottom left-hand side is an integrated system. If you get into an automated system, you may choose to make your own ice, just a fully automated system. It comes to you in a rotational molded, insulated tote, and it's about a 500-pound tote. They'll pick up the empty and bring you a new one when the ice is empty. It's made in blocks. It's made in slices for the airline industry. The blocks are shaved. The pellets go straight into a feeding system and then are actually blasted in 3 millimeter. These are the two most popular forms that you'll be using in the medical device manufacturing. Out of all those different sizes that you can possibly make, you're probably going to end up with either 3 millimeter or a block. And why do you choose one over the other? The block will give you microparticles. When you shave it, you'll end up with 0.3 millimeter size particles. Really good for thin, hard contaminants you'll find on tooling. Really good at taking off burrs and flash. Most popular in the medical device. If you're cleaning screws, some larger extrusion dies, you may want to get into 3 millimeter pellets because you're going to get more kinetic energy. That's usually good for thicker and brittle contaminants. So you get a little bit more aggression out of that. Those are the two most popular. You get a little bit greater flux density. You're going to get more strikes per square inch than you would using 3 millimeter. So it's good for getting into complex, difficult shaped geometries. Because it brings less kinetic energy, it's also gentler on substrates. So if you get into a variety of alloys that are on the softer side, the microparticles also are beneficial. So you pick a machine. You want a pellet platform on the left. In the middle are the block platform. The pellet platform are once again on the right. You pick that. Once you know what form of ice you want to do, then you just pick the machine that delivered that type of an ice. For those of you that have seen machines from a while back, if I were to stand next to these machines would just come. These machines in the front would just come up to a little bit past my waist, so they're not all that tall. For those of you that looked into it years ago, I mean, they used to come in on tractor trailers. They used to be taller than us. They used to be hauled around with tow motors. Not today. The lower right-hand corner shows a typical machine size, or the guy standing next to it. They've gotten a lot smaller, a lot less expensive, a lot quieter over the years. The theory and the process of how does this work? You can remember dry ice. Just remember the acronym ICE. There is an impact. It is very cold, and there is an expansion when it sublimates. Just remember ICE. There is some kinetic energy. Dry ice has very little hardness, so in order to get any work out of it, you got to get it accelerated pretty quick. If you notice on the chart, this is the Mohs scale of natural substances known to man, talc being the softest, the diamond the hardest. Dry ice is right up there with the soft side. So to get work out of it, you've got to get it moving at about 600 to 1,000 feet per second. That will bring some kinetic energy. Kinetic energy being measured, 1/2 the mass times velocity squared. Good to keep that in the back of your mind. You do have the ability when you take dry ice and you apply this process to your manufacturing of medical devices to control the amount of kinetic energy that you bring to the process. On an ambient substrate, this is probably doing 60, maybe 65% of your cleaning. So this is where you're going to get the biggest bang for your buck, where you make your adjustments in your velocity controls on pressure to control the kinetic energy and your particle size. Even if you choose to use a 3 millimeter, you're able to knock that down with splitters, or sometimes called fragmentation. You can knock down that particle size with some pins inside the nozzles that allow you to reduce the kinetic energy. Helpful when you get on a substrate that may be gentler. It is also very cold. There is a thermal effect to this. Dry ice, as we talked about before, for us in Fahrenheit, it's minus 109 degrees. It's the coefficient of thermal expansion and contraction of dissimilar materials. The contaminant is not the same as the tool steel or the mold base, the H13, the P20, whatever the mold's made out of. That dry ice will impact the contaminant. It will cause that contaminant to embrittle. it'll cause it to freeze, and it'll lose its bond strength. It'll lose its adhesion because it just got instantly frozen, and it just frees it up from the substrate. So you have cracked that contaminant with a little bit of kinetic energy. You freeze it, and then it lets loose. The higher the delta T that you get between the contaminant and the dry ice, which means the hotter the tool, the hotter the mold, the more the cold contributes. Got some test studies that show at 500 degrees C, which I don't think any of us are going to get there. Even if you're molding rubber, you might get into the low 200s. But the higher that delta T, the more this effect contributes to the clean. 500 degrees C, it's been estimated and calculated to be 50% of the clean. So translate that. If you clean something that's hot, you don't let it cool down, it will clean easier, it will clean faster. And if you're wondering what's the magic in that, the magic is the thermal property, the thermal effect of the dry ice cleaning is contributing more on a substrate that's hot. The last effect that come into play after I've cracked the contaminant with some kinetic energy, I've embrittled it instantly with the cold. On impact, that solid CO2 will phase to a gas. It's going to volumetrically expand, depending on where you are sea level, about 800 times its size. So all these little micro explosions go on the surface, and they just blow the contaminant off of the whatever that substrate is you're cleaning. So it goes back into a gas, and it's dry, and thus the name dry ice. And that's the magic of it. The kinetic energy is common to some other blasting media, but that thermal property, this expansion properties are very unique to the magic of dry ice. The dry ice comes in kind of a diagram here. You hit the contaminant, it shrinks it, it's cracked it, and then it expands. Let me just give you a little quick video of what that would look like in a simulation. That is what dry ice cleaning looks like. The dry ice is accelerated at high velocities. It is impacting the contaminant. It's traversing. It is embrittling the contaminant. It is phasing back to a gas, and it is blowing the contaminant off. That is the entire process. If you can understand those three aspects of it, you can then begin to adapt. How much kinetic energy do I bring to the substrate I'm cleaning now? You're running a hot runner mold, you're cleaning the cavities, you can go at it with a lot of kinetic energy. You get to the top of the hot runner system junction box, terminal strips, wires, you're going to want to lower the kinetic energy so you don't strip the insulation off of the wires. What are the common applications in medical device application with this dry ice technology? In-machine mold cleaning is definitely number one. In-machine mold cleaning at operating temperature is a device that rolls up next to the press. You interrupt the process and you clean the parting lines. He's cleaning the A half of the tool now. He'll turn around and clean the B half of the tool. He is cleaning all the off gases off of the cavities themselves, off of the vents. If the leader pins, ejector pins are part of the venting system, they'll clean those as well, likely relubricate them before they go back into process. Mold cleaning is often done just in an open environment with good filtration. Sometimes it's in a clean room. We've had success in what I call the ISO 8, the class 100,000. Somewhat depending on when you take the isokinetic probe into the room, what does the room read in a static state before we do a dynamic clean? If we walk out there and the room's reading 96,000, we're probably going to push it over. But if we walk out there and the room's reading 60, 70, we'll raise it a little bit, but it'll stay under 100. We're also working on some contaminant containment systems to contain those contaminants, because there are some people wanting to take this. They're starting to take molding into ISO 7. I do have one company that tells me they're using it in ISO 7, but I've personally not seen it yet. But I have seen it used in class 100,000 ISO 8 clean room. is a rubber mold. The off gas is here on the top left. The bottom left is the after. This is a job that took 6 to 8 hours to clean. They had to let the mold cool. They would then clean it. They had to heat it back up. They lost practically an entire shift. Now they do it in 30 minutes. The hotter the tool, the better. A great way to improve the quality and to do it quickly. This is a video of what it looks like to clean the mold and the cavities. To clean the vents, he's on the cavity cleaning it with the dry ice. You can see the dry ice stream. It turns into a gas, which you can also see as it strikes the surface. But it quickly allows him to clean both the A and the B half cavities. There he's cleaning the vents very quickly and cleanly. Variety of surfaces. We get into Class A 1s, 2s, and 3s. We get into highly polished tools. We get into highly polished rolls on extrusion lines, textured substrates, whether they're aluminum, whether they're tool steel. We can adjust the kinetic energy to adapt to the various are so small, so atomized, he's letting them go. This is the cooling roll. They are often cleaned with dry ice, whether they're embossed or just a straight cooling roll. They're highly polished, easy to damage those with some traditional cleaning methods. Cleaning screws, for those of you that mold with concerns of cross-contaminations between running jobs, cleaning screws is very popular. For this, the 3 millimeters bring a little bit more kinetic energy to the game. The diameter of the screw does matter. How thick is that plastic, particularly if you let it get cold, as in the example here. And crystallines seem to respond just a little bit better than some of the amorphous resins, but they clean up rather nicely. Another application on how to deploy dry ice in medical device manufacturing is oftentimes due to the volumes of the part. We end up with some low volumes, high value parts that end up with subtractive manufacturing. They are CNC machined. As a result, they get burrs. Those burrs are easily removed on most plastics with dry ice. The lower left is that's actually not plastic. That's a nitinol stent, which is deburred using the microparticles. The 3 millimeter pellets would damage that type of device very quickly. That's where the microparticles come into play. Some of the plastics we've cleaned and deburred are listed here. I'll let you read those. Some of those may be applicable to you. I think I've got a graph in here as to where those fall. There are some plastics that we do quite well with, but a lot of different medical devices are machined, and we will deburr them. Why are we using dry ice to do this? Well, you can tumble them. You can do it in a variety of ways. But dry ice is non-abrasive. It's not going to affect the geometry of that finished part. You see the before and the after pictures. There's no residual waste. As we talked about before, it sublimates. Sometimes you bead blast, use a variety of different things. Depending on the geometry of your medical device, you may end up with part of your blast media stuck in your medical device part, and you got another operation to get it out. Depending on what it is you're doing, what you're using as a media, like polycarbonate as a blast media, that has BPA in it. You can cross-contaminate medical device parts with some of the media that you use. Dry ice does not do that. It doesn't leave any harmful residues behind. You're able to target where you want to go on the part. I don't have to tumble or hit the entire part. I can manipulate the part or my nozzle just to focus on the particular area that needs to be either deburred or possibly deflashed if it's a molded part. Deflashing and deburring, just to give you an idea of what that looks like. This is a pretty short video that starts with deflashing of a part. It looks like a urethane type of a part. Then it goes into the deburring of a machined part. That kinetic energy, when you put most of the burr in time, when you get into the deflashing or deburring type of solution, instead of a mold cleaning, it gets automated. Beside the press, systems with robotics are often deployed. If it's an ongoing solution, then we will automate the deburring or deflashing of that particular cell. I got into it earlier. I was hinting to that not all things in the world deflash easily or readily. The type of plastic does matter. If you notice the rubbers and some polyurethanes that are on the chart in yellow and the blue, they don't deflash all that well. The plastics, you get up into the 90s, into the Rockwell R scale, they deflash quite well. You get anything into 3 digits very, very readily. And you can recall why. Kinetic energy is doing the heavy lifting when we deflash and we deburr. These softer urethane parts, rubber parts, have a tendency to just want to absorb that kinetic energy. But they don't deburr as readily. So it's more useful in the harder plastics for those in the 90 plus on the Rockwell R. For those that are softer, yes, you can dwell on it. You can get to that, the glass transition phase of that particular plastic with the cold or the dry ice. But it's going to take a little bit of time. So you're probably better off from that particular one to tumble it with some liquid nitrogen or another actual cryogenic deflashing technique on the softer resins. The integrated systems do come into play. If you can do them by hand, you can hold the part, you can fixture the part by hand, you can remove the flash, you can remove the burrs. If it's repeated, you may put a robot on it. And to fully close the loop, I can tell you when it's time to load more ice into the machine. And if it fits the production schedule, if there's a fraction of a body in the area that could respond to an alarm and it's time for ice, then you can manually load it. If it's fully automated, this is the machine that made the dry ice from earlier in the presentation. It makes the ice. It will load the machine automatically for a fully closed loop system that does not require anybody to manually load the ice. There's fully enclosed systems like on the right, which the blaster is integrated internal, and then there are larger systems on the left. Just to give you an idea, you can integrate the entire process. You can automate the entire process if it's necessary. I guess I come down to the end. Do you believe in the magic of dry ice? Now, there are several people in the medical device industry that do. I won't read the logos, but these are people that use dry ice in their process. Why? Because it's a proven technology in this industry. You can improve the yield. You will get better quality. It will extend the asset life of your molds. It'll reduce your cost. It'll help you with your environmental issues, working with VOCs. It is a very effective way, if not the most effective way, to clean a mold inside a press. And it's a very good way to deflash and deburr medical device parts. So I'm going to turn it back over to you, Paul, allow you to get into some questions and answers. I'll just toss this out before I do real quick. If you want somebody to stop by, an engineer to stop by and evaluate, hey, does dry ice appropriate for us? We're in a position to do that. If you want to send us specific, I've been trying to keep this around just dry ice, not necessarily a cold jet presentation, but if you want to send us sample parts, we have test cells here where we can do the testing for you, video it, and send it back. Or, like I say, allow our guy to come to you and just evaluate, do you have an opportunity to use dry ice in your facility? So, Paul, I'll toss it back over to you for questions at this point.
All right, thank you very much, Steve. Hey, that was fascinating. I know a heck of a lot more now about dry ice than I did before. So let's get some questions. Start with one here. From Tim asks, any data on cleaning precision optics? Wait, I can't speak. Hold on. Are there any data on cleaning precision optics, like lenses of sorts?
We have I'll just drop one name like Bosch. We have people there. I don't know what the tools are made out of. I have not visited there, but we have people cleaning optical grade tooling. I'm not even sure what the substrate is. I think they were using an Alcoa QC10 mold base, but I'm not positive. Yes, we have people doing that. It is definitely microparticles. It is not with the 3 millimeter. With that, you've got to control the amount of kinetic energy. With the microparticle systems, yes.
Okay. Let's see. Does the process remove all types of burrs?
The process is really good at removing flag burrs. If it's a rollover burr, it's definitely worth testing. Rollover burrs can have a very good adhesion, which can make it a little slower and difficult to get them off. So it is best to be a flag burr, rollover burrs. We need to test. But not all, but
okay.
most.
All right. Let's see. Albert asks, has wear been observed on molds that have special coatings, such as chromed or whatnot?
We clean all kinds of coated molds. Matter of fact, I've got a third-party relationship with Metco Salzer. Salzer puts DLCs, diamond-like coatings, on molds. If you were to look at their 80-page presentation, it's about 80 pages, presentation, you get about 3/4 the way through the presentation, there's a picture of a cold jet machine. We'll just say that they recommend dry ice to clean their coatings. Yes, I've cleaned several chrome-plated tools, whether they're on cooling rolls, whether it's on a screw or the mold itself. I would say if there's a chip, if there's a flaw in the chrome plating, the process will expose it. There's enough air pressure. We're propelling this with compressed air, that if there is a flaw in it, it will expose it. But probably needed to be fixed anyway. If it's not, if it's a good coating, we will not damage it. No.
Okay. All right. Another question here: will dry ice cause brittleness in a medical part after deburring? Does it chill the part, I guess, to make it brittle?
It will lower you're going to get you're not going to get the part all that cold, because if the burr doesn't come off almost immediately, the process probably is not working. Each resin has its own particular tensils and different parts, so I couldn't say specifically to his particular device. We'd be glad to test it and let him do that, but typically you are not dropping that surface temperature more than 5-10 degrees, so it should not be imparting a thermal stress. I do have tests where we put thermocouples in steel. We definitely do not stress the steel. But on a particular medical part, that would probably be a lot dependent on the resin itself, any additives, fillers that might be in it. I would be glad to sample those and allow a post-test to be done.
Okay. All right, Mike asked a good question here. One part spoke of cleaning molds line of sight. Another emphasizes saving time by not tearing down molds. How effective is the process reaching between inserts and such? Say down as little as, he uses dimension, down to as little as 0.0002 inches clearance.
You're getting down to the vent sizes now. We can get into very tight spaces, but I've got to hit it. I'm not hitting back plates. We are definitely doing a line of sight. The dry ice has to impact it. It's not even going to ricochet like if you had it offline, you're cleaning with sand. The sand will bounce off a wall, ricochet, and clean that back. I've got nozzles that go on angles, but as long as I can get the ice to hit it, we get into some very, very tight spaces. But I'm extending the production run to make it clear for those of you who are talking about molding, I'm cleaning the parting line. So eventually those off gases are places that I'm not hitting. You can extend ejector pins and various things and clean them up, but you'll have to degrease them, put grease back on them, because I'll take the grease off. But if I'm not hitting it, I'm not cleaning it. So sooner or later that mold does have to come out for a deep clean. I allow you to extend the production run. You're not finished with the run, but yet it's time you're about to get bad parts because you've made X number of them. You know when you get to X plus so many, that the cavities are getting fouled, the vents are getting clogged, it's time to clean, you can do all that and you can extend the run. But like I say, sooner or later you're going to get things dirty that I'm not cleaning, and you're going to have to pull it for a deep clean. People do use this process on a bench. When they disassemble the molds, yes, you can clean each part by hand using dry ice. At that point, you've got other alternatives as well. But yes, you can use this on a bench to clean up the various parts once you get them taken apart.
Okay, all right. Here's a good question. Can dry ice clean rust on water channels of mold?
Yeah, it'll take, once again, and dry ice is soft. This is one of the limitations and one of the nice things about dry ice all at the same time. It will take surface rust off. I see most guys using it to get the surface rust off of back plates. They're usually incorporating magnetic mold clamps, and they want that back plate to be as clean as possible. I'll take the surface rust off. However, if that rust has been on there long enough and it's pitted and it's now in the steel, I will not get the pitting out. It's there's a kind of a rule of thumb with blasting with dry ice. If it's on it, it comes off. If it's in it, it does not. But understand this is the positive side to it. That's the negative side, I guess. The positive side is it's good that it doesn't take the pitting off. Because if it took the pitting off, I just profiled that steel. I dimensionally altered that steel by just a few thousandths. But if my process was capable of doing that, we don't want to do it on cavities and vents, because now I will cause you to have flash. I'll be wearing out your parting lines and your shutoffs and your cavities, but it's too soft. So the bitter and the sweet of it is, yes, it'll take surface rust off, but it won't get the pitting off. It won't get rid of it. It's not aggressive enough to do that. But actually, that's a benefit for us.
Okay, Jorge asked a good question here. Do you know of anyone using dry ice for cleaning additive manufacturing residues?
I have that being tested as of the K-Show and am anxious to hear the results. I know there are some things left on a part. We are doing it right now. I can tell you it's in Europe. I can't tell you with who. But there is some surface prep, some part cleanup that is being done on those parts with dry ice. Definitely the microparticles, definitely the gentle side. I am very anxious to see how it's done. I have cleaned the nozzles on the printer, on the print device itself. We actually cleaned the print nozzle on the freeformer for Arbor, one of the trade shows. Their nozzle clogged. They were about to throw it away, and we grabbed it, took our nozzle, cleaned it with dry ice in about 3 seconds, and they go, I'll be darned. Put it right back on, and they did not throw that nozzle away. So from that side, I've seen what we've done in additive manufacturing. On the finished part, man, if I was doing this next week, I might have an answer. We're doing some testing now. If somebody wants to work with me on that, and we want to do some testing at your place or here, would welcome the opportunity to see how we can impact this, because I know sometimes just blowing the part off is not good enough, and that's exactly what I can bring to that's what dry ice can bring to the process. It can bring just a little bit more aggressiveness to that part finishing, and I don't think we're going to damage that part. So we'll be glad to try it.
Okay. All right. Here's a good question. Since you're sort of chilling a part when you clean it, the question is it possible for condensation to form on the mold face?
If you're cleaning a tool that's not on a thermolator, not hot, I guess here's what can happen if you become stationary in one spot on a tool, which you should be traversing. Let's just say for some reason you decided I got to get that off of there, and you sit on it. If you lower the surface of that mold below the dew point, whatever it happens to be that day with relative humidity, temperatures, and calculate dew point, you get it below the dew point, condensation can occur. That is possible. You flip the applicator on any dry ice machine over to air only, and you blow air, and you quickly make that disappear. It doesn't happen very often because a lot of the molds have thermolators on them. they're heated, and the surface, the traverse rate is going at such a rate that you're not dropping the temperature below the dew point. Once again, the dry ice is hitting the contaminant, and once the dry ice hits the contaminant, the thermal property is gone because the dry ice is sublimated. So some of it gets carried over into the substrate into the tool itself, but not a whole lot.
Right. Here's another question about lenses. A lens is made with a PC resin, and it's clear and transparent. Okay. Can dry ice be used to deflash without damaging the surface transparency?
On the actual lens itself?
Yeah, it sounds like, on the lens itself.
On the lens, if it's on the perimeter, I would have no issues with that, because I could definitely fixture and stencil where I didn't hit the lens. If I've got to hit the lens itself, I would definitely want to test that. I've not tried that on the lens itself. We have on the perimeters and done fine, but on the lens itself, I would just be concerned the kinetic energy that would be needed to remove the flash could leave a signature on the optical quality of the lens itself.
Mm-hmm.
But we've not done it, but I would have a concern for it and would want to test it.
How involved would a test be? If one of the audience
simply means a test is just reaching out to us and say, look, I want to send some parts to ColdJet. Give me the process of what you did them under, video it, or they come with it, or we come to you. Like I was offering before, I'm trying not to make this about ColdJet, more just about dry ice in the industry, but ColdJet has demo vans running all over the country, all over the world actually, where the guys will come to you for free. They'll evaluate, yes, you got a good thing for dry ice, or you don't. We will do a free demonstration. We bring the machines, we bring the ice, you have the 110 electric and the compressed air, and then we do a demo on your site. If you like what you see, we do a performance evaluation program where you can have the machine for 30 days, and you get your money back if you buy it. So for 30 days, you evaluate. All right, we had a successful demo. It passed the go, no-go gauge. Let's just see what the ROI is on this process. Let's just see the sustainability of it, repeatability. We'll do that. So that testing that I'm talking about, guys come here, they send parts here, or we just simply do all of it at the customer installation.
Okay, that sounds good. All right, here's a good question occurred to me. What's the storage life of dry ice?
Yeah, storage life is a real critter. That chart that I showed early on, if you keep the liquid CO2 at 300 psi, it's got almost an infinite shelf life. Once you put that liquid CO2 into a pelletizer and you have then converted the liquid to a solid, it's a vanishing commodity.
Mm-hmm.
That storage bin that the gas company delivers to you will last about a week, but even then, dry ice is going to sublimate at about 4% per day. So it doesn't have a shelf life like resin. For example, you take a delivery of dry ice on Monday, and for whatever reason you decide, we don't want to do this, and you come back in 3 weeks and say, go get that box of dry ice. You're going to open it up and think that, what happened? He sent me an empty box. It will sublimate about 4% a day. You got about a week to use it.
All right, we're running out of questions. Here's the last question, ladies and gentlemen. Where do I purchase dry ice?
You might be doing business with a dry ice company now if somewhere in your facility you're using gases. If you're using welding gases or some other type of gas in your process. Your Praxairs, your Lindys, your Continental Carbonics, your Air Gas. All the gas companies deal with dry ice because dry ice is just the solid form of a gas. So, you can buy it in small quantities at high prices at your local grocery store, probably pay $5 a pound for it. But you can buy it from a local gas company for probably about 25, 30 cents a pound. And they'll deliver it in that big tote. When it's empty, they pick up the empty, bring you a full, and over time you will learn how many totes do you order a week, and the rotation begins. just your local gas company. And if you find from purchasing, you may already be doing business with one.
Okay.
If not, we'll help you find one. We know where they all are, and we'll point you to the closest gas company.
Okay, we got one more question. I must have been sleeping here. Is it possible to obtain USP grade through dry ice?
Yeah, that'd be a question for your local gas company. I believe it is, but does your local gas company do that? The dry ice is pure. If any cross-contaminations are an issue, I would encourage a conversation with the dry ice company about cleaning the totes that they bring you. Totes get in some interesting environments. You're going to want to make sure, because the dry ice itself is probably going to get the green light. The tote itself may need to be cleaned before they put your ice back, that grade of ice back in it. I mean, these totes end up in foundries. They end up in a variety of environments, and the gas company picks them back up and fills them back up. Mm-hmm. On that one, I would sit down with a conversation with my local gas company, tell him what my requirements are, and we need to control this process, close the loop, not just from the manufacturer of the ice itself, but the transport vessel, the totes in which they're delivered in. We control that whole process to keep.
Okay, very good. All right, ladies and gentlemen, we've come to the end of the presentation. Once again, this webcast will be available for reviewing at medicaldesignandoutsourcing.com and the URL that you used today. One final message, you can follow Medical Design and Outsourcing on Facebook, Twitter, and LinkedIn. So this concludes our program. I want to thank Steve Wilson for the fine presentation and you, the audience, for your attention and the good questions. From the staff here at Medical Design and Outsourcing and ColdJet, we wish you all a good and productive afternoon.